Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we talked about microscopy-based techniques, XRD, SEM, TEM, AFM, and STM, which reveal where atoms and features are. Today, we turn to the complementary set of tools, the spectroscopic techniques that tell us what atoms are present, how they bond, and how electrons behave. Spectroscopy fills the gap between structure and property by revealing what happens inside the bonds, while diffraction and microscopy show how atoms are arranged. Spectroscopy explains how they interact, how vibrations, electronic transitions, and charge redistributions occur when matter interacts with light or particles. Each spectral response becomes a fingerprint of bonding, oxidation state, or defect configuration. At the nanoscale, confinement and quantum effects shift these signatures, making spectroscopy a crucial complement to imaging and diffraction in understanding material behavior. Let us start our discussion of spectroscopy with Raman spectroscopy, one of the most widely used vibrational probes in material science and nanotechnology. Raman spectroscopy is based on the inelastic scattering of photons. When monochromatic light, typically from a laser, interacts with a solid, most photons scatter elastically. No energy exchange. A small fraction exchanges energy with lattice vibrations called phonons. If the photon loses energy, it is a Stokes shift. If it gains energy, it is anti-Stokes. Plotting intensity versus Raman shift gives a spectrum where each peak corresponds to a specific vibrational mode of the lattice. Because bond strength, mass, and symmetry determine phonon energies, the Raman pattern serves as a fingerprint for chemical composition and crystalline order. The modern Raman system combines optics and precision detection. The laser beam is focused, often through a microscope objective, onto a micrometer scale spot. Scattered light is collected, passed through filters that remove the intense Rayleigh line, and then dispersed by a monochromator onto a CCD detector. In micro-Raman or confocal setups, we achieve sub-micron spatial resolution, allowing local mapping of stress, defects, or composition. Spatial stages enable in-situ heating or biasing, letting us watch changes in vibrational modes during processing. When dimensions shrink below the phonon coherence length, vibrations are spatially confined. This relaxes the momentum selection rule, causing Raman peaks to broaden and shift toward lower frequency. For instance, bulk silicon has a sharp optical phonon at 520 cm inverse, but nanocrystals show a broader red-shifted band as size decreases. Similar effects appear in zinc oxide, titanium dioxide, or graphene, where strain, edge, disorder, and defects modify phonon energies. By analyzing these spectral changes, we can estimate crystallite size, strain, and disorder in nanostructures non-destructively. Raman spectroscopy is among the most versatile analytical tools in nanoscience. In carbon systems, the D and G bands quantify defect density and ordering. In semiconductor or oxide thin films, Raman peak shifts reveal local stress and phase changes. Because lasers can be tightly focused, spatial mapping produces two-dimensional stress or compositional images. With in-situ Raman stages, we can track temperature-driven phase transitions or chemical reactions in real time. Thus, Raman links structural, chemical, and functional information within a single optical probe. While Raman spectroscopy probes lattice vibrations through light scattering, another powerful and complementary vibrational technique is infrared spectroscopy known as FTIR. FTIR spectroscopy measures how molecules absorb infrared light at specific wavelengths. Each absorption corresponds to a vibrational mode of a bond, stretching, bending, or twisting. Because each bond has a characteristic energy, the IR spectrum acts as a chemical fingerprint. For example, silicon, oxygen, silicon stretching modes appear near 1100 centimeter inverse. Carbon double bonded to oxygen bond at around 1700 centimeter inverse and OH near 3400 centimeter inverse. By recording transmittance or reflectance across wavelengths, we obtain a spectrum that directly reveals chemical bonding and surface functionality, critical for nanostructured oxides, polymers, and surface-modified nanoparticles. FTIR becomes especially powerful for nanomaterials because their large surface area amplifies vibrational signatures from surface bonds. In oxide nanoparticles, IR spectra can track the evolution of silicon OH and silicon oxygen silicon bands as sol-gel precursors condense. For metal nanoparticles stabilized by organic ligands, FTIR identifies the nature of capping groups, thiols, carboxylates, or amines. In polymers or composites, it monitors cross-linking and curing reactions. FTIR and Raman are complementary. Raman detects symmetric vibrations, while FTIR probes those that change the dipole moment, together providing a full vibrational picture. Both FTIR and Raman spectroscopy probe molecular vibrations, but they do so through fundamentally different physical interactions. In FTIR, infrared light is absorbed when a vibration causes a change in the molecule's dipole moment. This makes FTIR highly sensitive to polar bonds such as carbon, oxygen, OH, and SiO bonds. In contrast, Raman spectroscopy relies on inelastic scattering of light, which depends on changes in polarizability rather than dipole moment. As a result, Raman is particularly strong for symmetric or non-polar bonds like carbon-carbon or silicon-silicon bonds. Because of this difference, the two techniques are complementary. FTIR reveals dipole active modes, while Raman highlights polarizability active ones, together giving a complete vibrational picture. FTIR is generally free from fluorescence problems, while Raman signals can sometimes be obscured by background fluorescence from impurities or substrates. FTIR typically probes micrometer scale depth depending on whether it is used in transmission or ATR mode, whereas Raman especially confocal Raman, can achieve sub-micrometer depth and better spatial resolution, even down to tens of nanometers with advanced setups. FTIR collects spectra quickly and works well with powders, thin films, and liquids, while Raman offers higher spatial precision but slower mapping. In practice, FTIR is ideal for studying functional groups, surface chemistry, and coatings, whereas Raman excels in mapping, bond symmetry, crystal strain, and defect structures. When used together, these two techniques provide a powerful complementary view of bonding and chemical structure, making them essential tools in nanomaterials characterization. So far, we have focused on vibrational spectroscopy, which probes how atoms move. We now shift to optical spectroscopy, which probes how electrons respond to light. UV-Vis spectroscopy measures how much light is absorbed by a sample as the wavelength changes. In semiconductors, a sharp rise in absorption marks the optical band gap energy. In nanocrystals, quantum confinement shifts this absorption edge towards shorter wavelength as particle size decreases, a direct optical signature of nanoscale behavior. Metal nanoparticles such as gold or silver show plasmon resonance peaks that depend on their size, shape, and surrounding medium. By analyzing these absorption spectra, we can estimate particle size distribution, band gap, and optical quality of thin films or colloids. While UV-Vis spectroscopy tells us how a material absorbs light, photoluminescence reveals what happens after that energy is absorbed. Photoluminescence, or PL, measures the light emitted when excited electrons recombine with holes. A laser or lamp excites electrons to higher energy levels. As they return, they emit photons characteristic of the material's electronic structure. The PL peak position corresponds to the band gap energy, while additional peaks or tails often indicate defect states or surface traps. In quantum dots, PL shifts with particle size, providing a visual demonstration of a quantum confinement. PL intensity also correlates with crystal quality. A strong PL means efficient radiative recombination, while weak or red-shifted PL points to defects and non-radiative losses. Up to this point, we have discussed optical spectroscopies based on light-matter interaction. We now turn to electron beam-based spectroscopy for elemental analysis. Energy-dispersive X-ray spectroscopy, or EDX, is one of the most widely used tools for elemental analysis in electron microscopy. When a high-energy electron beam strikes a specimen, it can eject inner shell electrons from atoms. As outer electrons drop down to fill these vacancies, they emit X-rays whose energies are characteristic of specific elements. Each element has unique K-alpha and L-alpha emission lines. These serve as precise fingerprints for identifying which elements are present. Because EDX detectors measure the intensity of these X-rays across different energies, the resulting spectrum shows distinct peaks corresponding to the elemental composition of the region under the beam. EDX is typically integrated with SEM and TEM systems. In SEM, the interaction volume is on the order of micrometers, whereas in TEM, it can be as small as a few nanometers. allowing spatially resolved compositional mapping. Though semi-quantitative, EDEX remains a rapid, reliable and non-destructive technique for verifying stoichiometry, detecting impurities and studying elemental distributions in nanomaterials. While EDEX tells us which elements are present, it provides limited information about how those elements are bonded. XPS fills this gap by revealing chemical states. X-ray photoelectron spectroscopy or XPS is a surface-sensitive technique that tells us which elements are present and how they are bonded chemically. When X-rays strike the sample, they eject core-level electrons by the photoelectric effect. The kinetic energy of these emitted electrons is measured, and from that we calculate its binding energy using the relation bonding energy is equal to h nu minus Ke minus phi. Because each element has characteristic core level energies, the resulting peaks serve as elemental fingerprints. Even more, small shifts in the peak position, called chemical shifts, reveal oxidation states and local bonding environments, such as differentiating between silicon 0 and silicon 4 plus in oxides. Since the emitted electrons come from only the top few nanometers of the surface, XPS is inherently surface sensitive, typically probing depth of 5 to 10 nanometers. In summary, XPS links elemental composition to electronic structure, providing crucial information on chemical states, surface reactions, and a thin film interfaces. Beyond elemental identification, XPS reveals how atoms are bonded and what oxidation states they occupy. Small shifts in peak positions reflect changes in electronegativity, allowing us to distinguish, for example, Fe2 plus from Fe3 plus or Ti3 plus from Ti4 plus. When combined with controlled argon ion sputtering, XPS can remove material layer by layer and record spectra at each depth, creating a chemical depth profile through the film. This hybrid approach bridges surface and bulk information, showing how oxidation progresses or how interfaces evolve during annealing. In essence, EDX gives us elemental composition, while XPS refines the picture by adding chemical and electronic detail. EDX and XPS provide elemental and chemical information near the surface. When we need extreme sensitivity or depth profiling, SIMS becomes the tool of choice. SIMS uses a focused primary ion beam, often O2 plus, CS plus or AR plus, to sputter atoms and clusters from a surface. A fraction of those ejected species are ionized. Their mass to charge ratios are measured to yield a mass spectrum. Because the signal strength extends to parts per billion, SIMS is the most sensitive of all compositional probes. By continuously sputtering while recording spectra, we can obtain depth profiles with nanometer resolution, ideal for dopant distribution in semiconductor or multi-layer films. However, SIMS is a destructive and quantification requires standards. In combination with XPS and EDX, it complements the chemical composition picture from surface to bulk. So far, all the techniques we discussed characterize materials after processing is complete. However, many critical processes occur dynamically. In-situ characterization allows us to monitor these processes as they happen under relevant temperature, field, or chemical environments. By integrating heating stages, biasing holders, or environmental cells inside microscopes, we can watch crystal growth, alloying, oxidation, or stress evolution in real time. This approach connects the cause, external stimulus, with the effect, structural or chemical change, providing a true kinetic picture rather than a post-mortem view. Transmission electron microscopy offers a unique platform for in situ experiments because it combines high spatial resolution with controlled environments. Modern transmission electron microscopes can host miniature reactors. In situ TEM holders incorporate microheaters or electrical contacts, enabling imaging during heating, current flow, or stress application. We can directly see nanoparticle centering, diffusion, or domain wall motion. In environmental TEM, a gas or liquid environment surrounds the specimen, allowing observation of oxidation, catalysis, or electrochemical reactions while maintaining atomic resolution. For example, gold nanoparticles reshaping under CO exposure or battery electrodes undergoing lithiation have been visualized frame by frame. The resulting videos reveal rate-limiting steps and metastable intermediates that are invisible in conventional TEM. In situ experiments allow us to observe changes during external stimuli. Operando characterization goes one step further, probing materials while they perform their intended function. Operando means studying a material while it performs its function. For instance, following phase evolution in a battery electrode during charge, discharge, or monitoring catalytic surface species while the reaction proceeds. This approach integrates its structural probes such as XRD or TEM with property measurements like conductivity or reaction rate, producing a true structure property correlation. Correlative characterization extends this idea. The same microscope region is examined sequentially by TEM, AFM, Raman, or XPS to gather complementary information on structure, chemistry, and functionality. Together, operando and correlative methods reveal not just what a material is, but what it does and how that changes under realistic conditions. As characterization tools become faster and more automated, they now generate enormous volumes of data, gigabytes of TEM images, Raman spectra, or XRD patterns from a single experiment. Manually analyzing such datasets is slow, subjective, and often limits how quickly we can iterate in the lab. Artificial intelligence, especially machine learning and deep learning, provides a transformative way to extract knowledge automatically. By training neural networks on labeled datasets, AI can recognize subtle and complex features, grain boundaries, dislocations, phase domains far faster and far more consistently than human observers. This dramatically accelerates the feedback loop between synthesis, characterization, and modeling, ultimately enabling closed-loop materials discovery. Machine learning already permeates nearly every branch of characterization. Convolutional neural networks classify phases from diffraction or microscopy patterns. Clustering algorithms decompose overlapping Raman peaks and reinforcement learning is beginning to guide autonomous microscopes that tune, focus, exposure, and scan paths in real time. The emerging frontier is multimodal fusion, where models learn jointly from structural, chemical, and functional data to predict material behavior with higher fidelity. So, AI is shifting us from mere data collection to true knowledge generation, laying the foundation for self-driving laboratories.